Yeah, my name is Jack Dillon. I'm the equipment engineering manager for global operations and technology here in Wilmington for analog devices. Uh, One of my primary responsibilities is improving the performance of the equipment that we have here and also improving the yield or the quality of the product leaving the equipment. So I'm just going to walk through a couple of examples. And now, there we go. Okay. Okay. So just to give you a little background, actually a lot of this presentation is background, but we're going to start. Analog Devices has 4 internal wafer fabs. We also use a number of foundries, but the internal fabs are running what we call more than more technologies. We're not doing the 5 nanometer, 7 nanometer stuff that like TSMC or Global Foundries does. We do more the difficult, challenging, low volume processes that have high margins. And that's what our focus is on. So we have 4 fabs, one in Camas, Washington, one in Milpitas, California, one in Limerick, Ireland, and one in Wilmington. In 2019, the Wilmington fab shipped over 560 million die. We have over 400 major production tools, which is large for a fab that puts out the number of products that we do. We run over 1,000 products here in Wilmington. And on top of being a manufacturing site, we also do our own product and process development. The actual development is funded from the manufacturing operation. So we're really a fully self-contained operation. So some of the challenges we have, like in any manufacturing environment, there's tremendous cost pressure. In order to maintain your cost, you have to have very short cycle times and your yield has to be high. In order to achieve cycle time, you need reliable equipment, and stable process, and an optimized operation. And this is really where we spend a majority of our time is pretty much on these three things. As far as yield goes, if you saw, we run over 1,000 products here. And these are very complex processes, and we have subtle variations in film thickness or etch rates, uniformities, critical dimensions. It can result in electrical performance degradation of the final product when it leaves. Our cycle times can be long, up to 6 months for some products. So in many cases, when we do have a yield event, we don't find out until it gets to the end of the line or electrical test. Which is a horrible time to find out, that you've been making bad product for 3, 4, 6 months. It's not really you want to be. So we put a lot of engineering controls around our processes to make sure that things are going well. And with all these products and processes that we run, the chamber conditions, I'm an etch guy, so I'm always talking chambers, but it could be a diffusion furnace, it could be an implanter, it could be any processing tool. We have a lot of variations, so it's extremely difficult to maintain tight process control when all these conditions are varying. And as far as from a cost perspective, because that's really what drives a lot of this, one scrap wafer cost between $900 to $1,200. A little bit more on that later. So one of the things we started looking into is machine learning. What we've discovered is the fab equipment supports limits monitoring. So, during our recipes, we monitor the gas flow, we monitor the pressure, temperature, whatever the critical parameters are. And we know about these. So, if those go out of tolerance, the tool alarms and the lot stops. So that's easy stuff. But we've run into a number of problems where we don't have any visibility to it. There's 3 examples I list here: an unconfined plasma and a plasma etch system, unstable beam and an ion implanter. Those are 2 I'll cover. And then there's also something we were working on with Ash. I don't know if Ash is on the call, from Analog Devices at the Analog Garage, detecting hotspots and photolithography tools. I'm not going to go into that one since I believe Ash is probably going to talk about that later.
Yeah, and just a little bit of background. So Chris Lang is doing a 2-year research project on the plasma etch and ion implanter. And then Ash, who Jack just mentioned, is a PhD that's at Analog Garage in Boston, PhD. And so he's looking at this other problem. And this has been a really great collaboration, because we've had Ash inside Analog Devices as a data scientist working on the project, and he's done some really interesting things with Chris, which you'll hear more about in next week's presentation. So just a little preview of next week. So thank you. Sorry, Jack.
No worries. Okay, like I said, we haven't been able to detect this until now. So the expected results, we want to improve the yield. Actually, I'm going to speed this up a little bit. I think you're right, Bruce. We want to capture some of these silent events, and we want to lower our cost, and we want to improve the device reliability. Here's our, in order to run these analytics, we have to have the infrastructure to support this, which up until recently, we did not really have. We could get the data and then process the data after the fact, but we really want to do it as close to real time as possible. So this is just an overview of our system, and the one that we're the most interested in is the one on the left here. I can't get my laser pointer to work either. So what we did is we added here's our processing tools in the bottom left, which is process tool SEC serial HSMS. The SEC serial HSMS is industry standard for getting data from a fab processing tool. So we run that into our automation system, which used to have basic limits monitoring, and we recently modified that so we can run Python or R on the data as it's coming in. So the 2 examples I'm going to talk about are an issue we had in ion implant, and the second will be an issue we had on one of our oxide etch tools. I don't know everybody's background, but I just figured I'd give just a really quick overview of the ion implant process. So ion implantation is one of the fundamental processes we use to make semiconductors. So if you look at raw silicon, it's neither a perfect insulator or perfect conductor, hence the name semiconductor. But by adding dopant atoms to the silicon crystal structure, we can change the electrical properties of the silicon. So the function of the implanter is to allow the dopant to be precisely controlled as far as dose going into silicon, and also the depth at which we drive the dopant atoms in. And this is a very simplistic view of an ion implanter. If you look at the graphic here, you'll see the ion source. Okay, what we do is this whole system is under high vacuum, and we flow some gas into the ion source, and then typically with a plasma flood system, we ionize this gas, and then we excuse me. The ions are extracted from the ion source using electromagnetic fields, and it's directed into what we call the analyzer magnet here. As you can see, the analyzer magnet takes a right angle and goes down to the beam line. This magnet is massive. It's probably on our tools, probably about 4 tons. On the larger implanters, it's probably up to 6 tons. The purpose of this magnet is as the ions of a particular mass exit the ion source, the analyzer magnet is specifically tuned for that species going through. So the heavier ions will hit the left wall here, and then the lighter ions won't make the corner. So the analyzer magnet is specifically tuned to get these ions to bend around the corner and only the ions of interest. Then we electrostatically accelerate that, and then we use basically an electromagnetic lens to kind of steer the beam beyond that. And then the beam is then focused onto the wafer, and it's spun on this rotating wheel that's grounded electrically. And by varying, the acceleration voltage, that in our case it's 200,000 electron volts. By varying these parameters, you can tightly control the atoms that you want to, the ions you want to dep into the implant into the wafer, and then also the dose. And this is what we call the wheel chamber. The wheel here is this is what holds the wafers. The robot loads the what we call, these are heat sinks effectively, and the wafers sit on the heat sinks. And this wheel spins it at 1250 RPM. It also scans from left to right in the x-axis here. So this is spinning and then going back and forth as the beam comes through. On the right picture, you'll see that red arrow, and that's the direction of the beam coming through. So this is actually quite the mechanical marvel, but I'm not going to waste any time with that. So on to the problem. This is the recipe that we run on the implanters. We scrapped, I think it was 150 wafers. And I'll show you the trace, but this is one of those situations where there was noise on the beam current trace of the on the beam stop, and it was enough to alter the dose, so we weren't getting the dose we expected in this, which ended up scrapping all the wafers because it would not pass electrical test. The root cause was determined to be a poor ground connection on the beam stop, which is not a place that we spend a lot of time, so it was a little difficult to find. But I've included 2 traces here. On the left is the good plot. This is what a normal trace would look like. The blue trace is the scan position. As I mentioned, that wheel went back and forth on the x-axis there. This is the position of the wheel in that direction. And then the red trace is the beam current. So we're monitoring the current of the beam as this is all spinning through. What happened was, if you look at the right trace here, we started getting this noise on the beam current signal.
Yeah, could you just explain why you vary the beam current as the wafer position?
Yeah, we're actually the way it works, we are spinning the wafer in front of the beam stop. So as this is rotating through, the current will vary as measured. So it's kind of a unique setup. Normally you would have a single wafer tool where you could measure the beam current directly, but in our case here, we have to measure it as it's spinning through the wheels. So this signal here is actually integrated from the current that we pick up from the beam stop. And that's why we have this waveform, because we're actually blocking the beam at certain points in time. And like I said, on the right here is the problem child here. It's one of those things, if you look at the plot, you say, well, this is a pretty easy problem to solve, until you try to solve it. Oh, okay. Any questions on that? Okay. All right. So here's our second.
Sorry, Jack, I have a quick question for you.
Sure.
Sorry. So how much does the shape of that good plot on the left vary? Like, how much variation is there to be considered good?
That's a great question. It's also one we struggle with a little bit. One of the problems we have, and these are older technology tools, so they use a serial interface, which is slow, certainly compared to an Ethernet connection. So we can't quite get the sample rate we want. In this case here, this is a slower scan speed, so we're able to get a decent trace. But the question you ask is, we have our implant engineers who look at these traces all day. We run into cases where we say, not so sure on this one. Is this good or is this bad? It's which is part of that. Probably one of the biggest challenges through both of these projects is we generally get good wafers out, because that's the whole goal. We don't have a tremendous amount of data from either bad wafers or cases like this beam current instability here. So it's a big challenge, and I think that's the part that makes this whole process take so long. It's just trying to sort through the data and find out what is good and what is bad.
Got it. And if I could just ask one more quick follow-up. So
Sure.
what is the ground source of truth?
What is the ground source? What?
So
I'm sorry.
what is the ground truth? Like, how do you determine ground truth for good and bad?
It really comes down to, well, first of all, we have historic data as far as we know. Once this product gets to e-test, this plot on the right it's going to be bad.
Okay, so there is a downstream test that will tell you
Exactly.
definitively. Okay, got it.
Yeah, we don't have an inline test that will really capture this. So this is one of those. It has to get to e-test before we figure it out.
Got it.
What's the lag time between this process step and e-test typically?
It varies quite a bit, because we'll do a number of implants during the process, but it could easily be 3 months. Those are the ones you really want to avoid. If it's near the end of the line, you'll get that feedback very quickly. If it's the beginning of the line, you're going to be running a long time before you realize what's going on. Okay. All right. The plasma etch. And so what we're doing here is, if you look at the graphic on the top right here, what we're trying to do is etch away this oxide, the silicon dioxide here. Silicon is the substrate, and then we have an oxide here, and then we put photoresist on areas that we don't want to etch, and develop out these openings where we etch the silicon. So we use a plasma etch system. It's called a reactive ion etch in this particular case, and it's a chemically reactive plasma. So the picture at the bottom here with a nice purple glow, that is a wafer in an oxide chamber being etched. And the reactive ion etch is a combination of a chemical etch and an ion bombardment. The ion bombardments assist in the etch. What we're looking for is we want to etch down into silicon dioxide, and we want to stop on the silicon. We don't want to over etch into the silicon, which is going to cause us problems. So what we do is we monitor the plasma, and we use optical emission endpoint to monitor the light emitted by the plasma. And by looking at specific wavelengths of the material we're etching away, we can determine when we hit this this breakthrough step. So we've completed our etch of the silicon dioxide, and we're down into the silicon, so we know when to stop. So here's another one of these examples of we made a lot of bad product before we figured it out. This is, explain this trace a little bit. This purple trace is the optical endpoint signal that we would normally look at. And this is the one of interest. The other ones are just more to make a point. But these are wafers that ran consecutively. We'll run a lot of wafers, up to 25 in a cassette, and they'll be processed in, we put them in a load lock so they stay under vacuum the entire time, and then we transfer those into the process chamber for the main etch. And if you look at the purple trace, you can see it's relatively flat, and then you'll see a drop off. That is when we achieve that breakthrough step. So at this point here, the color of the plasma actually changes, and we see that we're down to silicon. What we tend to do is we tend to over etch it a little bit just to make sure we've cleared all the material out that we want to. So this is wafer number 7, and then we go into wafer 8, and things just go bad on us. So if you can see, this purple trace went from this to saturated. It just went to full scale. The problem with these endpoint signals is there's no alarm monitoring. It's just reporting back. There's a lot of valuable information in this. And we also see some activity in the sawtooth tune. There's an RF matching network that the RF energies would actually ionize with the gas. So we have to match the generator impedance to the chamber impedance. We use that with an RF match network, and this is one of the components in the network. Its physical position. If you can see from the good wafer, you can see it's nice and flat. When it hit the breakthrough step, it moves to a different position, and everything's looking really good. Over here, the position just starts hunting and doesn't really know what to do. We also see this this orange trace. This is reflected power. That's what the power that gets reflected back into the generator, which means your load is mismatched. But even if you look at the scale, we're around 5 watts. The alarm limit on this is 10 watts. So it's not unusual to have a little bit of elevator reflected power. So this was one of those silent events. We killed 357 wafers. And if you remember from the first slide, we're running about $1,000 per wafer. So this is a very, very expensive event for us. The only good news is we got a lot of good data out of this, which my boss is not impressed with. All right, that's pretty much it on the 2 problems, and then we can let you guys, either ask questions or discuss